4-4, graphing a function rule. Our objective for this section is to graph equations that represent functions. And my essential understanding is that the set of all solutions of an equation forms the equation's graph. A graph may include solutions that do not appear in a table. A real-world graph should show only points that make sense in the given situation. Okay, so we're going to start off graphing the function rule y is equal to negative 2x minus 1. So, might not know this yet, we'll spend a lot of time on it next chapter, but this is the equation of a line. So before we get to all the tricks about how to graph a line and how to graph other special kinds of functions, there is one basic method that you can use to graph any function, and that is to make a table. So if I want to make a table, I'd start with an input. Then I would plug it into my function, which in this case is y is equal to negative 2x plus 1. And then I would get some sort of output pair, and I would write it as x comma y. And then whatever that pair happened to be, I would put it onto the graph. Okay, so we're going to do my input. We're going to pick an input. We're going to do a calculation to get my output. And then I'm going to have my ordered pair as an output. So let's start with negative 1. So y is going to be equal to negative 2 times negative 1 plus 1. When I do this, I get positive 2 plus 1. So y is going to be equal to 3. So my input is negative 1, and my output would be 3. So on my graph right there, I go left 1, up 3, to the dot. Okay, so there's my first point. Try another point, 0. So that's y is equal to negative 2 times 0 plus 1. Negative 2 times 0 is 0 plus 1 gives me an output of 1. So for 0, I get an output of 1. Let's try one more. A little more room. Okay. So for 1, y would be equal to negative 2 times 1 plus 1. That's negative 2 plus 1, which would be negative 1. So for an input of 1, my output was negative 1. So for an input of 1, my output was negative 1. Let's do one more for 2. Okay. So again, I do y is going to be equal to negative 2 times 2 plus 1. That's negative 4 plus 1, which is negative 3. So my input is 2, my output is negative 3, and I can put that on my graph by going 2 right and 1, 2, 3 down. Right? So now all I have to do to graph my function is to take all my dots and make a nice smooth line that goes right through them. Okay? Should be relatively straight, but we get the idea. Okay? So that would be the graph of the function rule negative 2x plus 1. Okay? And this method of making a table, plotting points, will work for any function that we want to graph. Anything. Okay? Now, as we go forward, we're going to learn little tricks to make graphing faster for whichever function we're going to graph, but always we can fall back on this method if you have to. Okay, so my gotta problem. So let's try to make this a little bit better, and we're just going to make a smaller table here with an input and an output. So when I want to graph x is equal to 1/2 times 1/2 x minus 1. If I plug in, let's plug in numbers that actually work a little bit better with that 1/2. Let's start with 0. That gives me negative 1. If I plug in 2, that would give me 0. And if I plug in 4, that would give me 1. Okay, so 0, negative 1. There's my first point. 2, 0. There's my second point. And 4, 1, There's my third point. If I wanted to, I could plug in other numbers like -2, which would give me -2. And I have, obviously, a nice line going like that. Okay. When you graph a real-world function rule, choose the appropriate intervals for the value on the axis. Even every interval on an axis should represent the same change in value. If all the data is non-negative, show only the first quadrant. So for these graphs, right, I have all four quadrants, 1, 2, 3, and 4, right? We have positive and negative, okay? But when I have a real-world situation like this function rule that W is equal to 146C plus 30,000 represents the total weight in pounds of a concrete mixer truck that carries C cubic feet of concrete. So my input into this function is going to be concrete, okay, cubic feet of concrete. It doesn't make any sense for me to say, oh, this truck is going to carry -20 cubic feet of concrete, right? There's there's no logic in making C negative, okay, with this situation. Okay, so when we make this graph, we're only going to graph the first quadrant, and we'll talk about the graph in a second. But let's do some calculations to figure out W, or to figure out what I'm just going to pick for C and what I'm going to pick for W. Okay, so my input to this function, so I'm going to make a table, and my output to the table is going to be W. So my input is going to be C. What I'm going to calculate is that W is equal to 146C plus 30,000. And my output is going to be an ordered pair, which is going to be little c, comma, W. Okay? So here's my table, just like that. Let's start with 0. That would be W is going to be 146 times 0 plus 30,000, which is just 30,000. So for 0, my output is 30,000. Okay, so if I don't carry any concrete, then the total weight of the mixer truck is going to be 30,000 pounds. Makes sense. Truck still weighs something even if it's empty. Now I could plug in any value that I want. Okay, but I want to make a model that goes up to 200. That goes up to the capacity of the truck. That goes up to 200 cubic feet. So I could plug in 1, 2, 3, 4, okay? But if I want to get a nice model that goes all the way up to 200, okay, let's break it down into numbers that are, a, a good distance away from each other that'll get me up to 200. So let's do 50, 100, 150, and 200 as my inputs. So my equations would be 146 times 50 plus 30,000. And when I use a calculator to get this answer, I get 37,300. So my input is 50. My output is 37,000. Ugly 3. 37,300. Okay. Now, did you have to pick these numbers? No, you can pick any inputs that you want. Kind of makes sense to me to go by 50s, so I only have to do 4 calculations, and I'll get a nice data to make a nice graph. 146, that's a 6 too, times 100 plus 30,000 gives me input of 100, output of 44.6. Here we have 146 times 150 plus 30,000, and that gives me 150 and 51.9. Okay. And these numbers, right, you can get just from doing a calculator, right? 46 times 150 plus 300. Okay. And finally, oops, 146 times my 200 plus 30,000 is going to give me an output of 200, comma, 59.2. Okay, so here's my data. And like I said before, it doesn't make any sense to make negative numbers. So let's make a nice graph with just the first two quadrants. Okay. So C is my independent variable. W is my dependent variable. So C is on the x-axis. C is the input. It goes on the bottom. Weight is my output. Okay. And I'm going to make this go by, again, I'm not going to make a graph with every single point on it. I'm going to make the axis the same interval. So I want to make these interval of 50, right, which is my input and output. 150, 200. Okay. And here, let's go 20,000. Again, you want to keep these the same. Okay. So I'm going to go up by 20,000 on the y-axis, up by 50 on the x-axis. Okay. And you can set each axis to do whatever you want. It will affect the picture that you get, but the data is still going to be the same. So my zero coordinate was 30,000. At 50, I get 37, which is about right there. At 100, I get 44, so that's going to be over 40 right there. 150, I get 51.9. So you can see that even though my points are not super accurate and right below 60, right, I still get data that forms a general line like this. So function rule W is equal to 8g plus 700 represents the total weight in pounds of a spa that contains g gallons of water. So what is a reasonable graph of the function rule given that the capacity of the spa is 250 gallons? So again, when you have a problem like this, you should pick numbers that are going to work well with the data that we have. So I would say I would put in maybe the same, maybe go up by 50 again. Maybe go 0, 50, 100, 150, 200, 250. Okay. And of course, it's going to be a linear, it's going to be a line again. And I would put the x-axis maybe going up by 50, and the y-axis maybe going up by 500. Okay, because that way we could start not at the bottom, right? We'll start a little bit over the first line, and then we'll get a nice little picture of what all the graph is going to look like without going too far off. Okay, when there's no gallons of water, the 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 weight of the spa will be 700 pounds, and when we fill it up to 250 gallons, it will be 2,700 pounds. Okay, so going up by 500 would give us a nice. It'll cover off the whole range of the thing. Okay, and that's what I said. The weight at 0. Let's do this. If g is equal to 0, then the weight is equal to 700. Okay. Right? Because we plug 0 in there, we get 700. Okay, so back in this problem right here with my truck. Truck can contain any amount of concrete from 0 to 200 feet, like cubic feet of concrete. So we could have had 27.3 cubic feet. We could have had 105 and 2/3, right? Any any place on this line, right? The function is defined. Okay, so we could have any amount of concrete, and that makes sense too. Is that you're filling up a truck, you could have any amount of concrete in there, right? You could stop filling it up whenever you want. Um, you just can't go over 200 because that was the max. Okay? So uh, some graphs, you can connect all the data points from the table because any point between the data has meaning. Sometimes you can do this. Some graphs may be composed of, and sometimes you can't. Some graphs can be composed of isolated points. Okay? So when we have a continuous graph, that is when we have a graph that's unbroken. Okay, we have one solid line. If we have just data points and we don't connect the line in between them, it's called a discrete graph. Okay? So we have continuous and discrete. So with this question, problem 3, we're going to identify the difference between a continuous and a discrete graph. So a local cheesemaker is making cheddar cheese to sell at a farmer's market. The amount of milk used to make the cheese and the price at which he sells the cheese are shown. Okay? So write a function for each situation, graph each function, and is the graph continuous or discrete? Okay? So let's make a function. So first, the making the cheese. 1 gallon of milk makes 16 ounces of cheddar cheese. So if I want to make, we'll call it a wheel of cheese, right? So if I want to make the the cheese, I would take 16 times 1 gallon times the number of gallons of milk. Okay. So if I want to make a table, my milk is going to be my input, and my wheel of cheese, or the amount of cheese I get, the weight of the cheese I get, is going to be my W. So if I have no milk, I'm going to get no cheese. If I have 1 gallon of milk, I'm going to get 16 ounces of cheese. 2, 32, 3, 48, and so on and so on and so on. So if I were to graph this, obviously, again, I'm not going to make it negative. So I'm going to make my milk gallons on the bottom, right? So milk, okay, and weight, okay? And this is going to be in ounces, and this is gallons. So 1, 2, 3, 4, 5 gallons. And my ounces, let's go 10, 20, 30, 40, 50. Okay, so we start at 0, 0. 1 gives me 16, 2 gives me 32, and 3 gives me 48. So not a perfect graph, but we see that I can make a line with this because can I put half a gallon milk in? Sure. That's going to make me 8 ounces of cheese. Can I put 2.5 gallons of milk in? Sure. Okay, so you are allowed this function, and you kind of have to use a little bit of logic to decide that, but this function will let us plug in however much weight we want. Now, the amount of money that he makes from selling the cheese depends on the number of wheels of cheese he sells. So the amount I make is 9 times the number of cheese wheels. Okay? So again, we're going to make a table. So n is my input. The amount I make is my output. If I make 0, I don't make any money. If I make 1, I make $9. 2, 18, and 3, $27. Okay. So again, let's make a little graph. My x-axis is going to be wheels sold. My variable a. My my y-axis is going to be dollars. Okay, so we're going to go 1, 2, 3, 4, and we'll go 10, 20, 30, $40. Okay, so at 0, you make 0. At 1 wheel of cheese, you make $9. 2, 1, 2, 3, 4. At 2 wheels of cheese, we make $18. 3, $27, and 4 would be $36. Now, here's the question, do you connect the dots here? This one The answer would be no, because this farmer or this cheesemaker is selling each wheel of cheese. So he doesn't have half wheels for sale. He only sells the wheels whole. And you really don't go into, think about a supermarket, right? You don't go to the supermarket and just take a tiny piece of a wheel of cheese and then go buy that. No, you can go buy smaller things, but if you're going to buy the whole wheel, you buy the whole wheel. You can't split it up, okay? So this particular cheesemaker is selling each wheel, so we cannot connect the graphs because this farmer, he doesn't sell a half wheel of cheese. He doesn't sell one and a half, okay? He only sells whole wheels. So this is going to be a discrete graph, but the amount of cheese that he could make is going to be continuous. So let's just look at these and see which one will be continuous and which one will be discrete. Uh, the amount of water in a wading pool in gallons depends on the amount of time the wading pool has been filling. So if you can visualize that situation, you could stop filling the water at any time you want. You could stop filling it at 1 minute, 2 minutes, 3 minutes, half a minute, 5.5 minutes. Okay, you can stop selling anytime you want, so that is a continuous function. So the first one is continuous. For B, the cost of baseball tickets in dollars depends on the number of ticket bought. And this is clearly discrete because you can't buy half a baseball ticket. It doesn't work like that. So the cost for baseball tickets, the amount you spend is going to be 16. They're $16 each. Okay, can't rip it in half and buy an $8 ticket. So the function rule graphed in problems 1 through 3 represent linear functions. So all the stuff we've done so far has been aligned. This technique also works to graph nonlinear functions. When a function rule does not represent a real-world situation, graph it as a continuous function. Okay? So the only time that we are going to break functions into this discrete function where we have just dots and we don't put a line through it is when we can clearly see that the situation is that works for the situation, especially for the gotta problem, right, for part B. If you just have an equation, we always graph it with a line. Okay, so we never assume, and unless somebody actually tells you that, we never assume that the function is a discrete function. We always assume that it is continuous. And a best way to draw a function until you learn all the tricks for each function and talk about things like transformations and vertical shifts, horizontal shifts, things like that in Algebra 2. Before we learn all that stuff, the best way to graph a function is to just make a table. So I have my input. I'm going to do some calculation, and I'm going to get my ordered pair output. Okay, so I'm going to input. We can input anything, okay, but in order to get a nice picture of this, I'm going to start inputting negative numbers. Okay, that turns into the absolute value of -4 minus 4, which would be 0. Whoops, the answer is 0, so it's -4 is my input, 0 is my output. Okay, so this equals 0. Okay, let's plug in -2. So that's the absolute value of -2 minus 4 is going to equal to 2 minus 4, which is going to be equal to -2. So that's going to be -2 comma -2. Okay, well then, let's plug in 0. Absolute value of 0 is 0, minus 4 gives me -4, so there's my next point. Let's plug in 2 and then plug in 4. So that's the absolute value of 2 minus 4 gives me -2 again, which is okay. Oops, we want 2, -2. And finally, absolute value of 4 is +4, minus 4 gives me 0. Okay, so I can clearly see that just plugging in the numbers, doing the calculation, is going to give me my y values. Okay, so let's graph it. So we have -4, 0. -2, -2, 0, -4, 2, -2, and, whoops, -2, that was 3, -2, and 4, comma 0. So if you look at this graph, I'm definitely going to connect the dots, and you see you get kind of like a V, okay? Which is what absolute value functions look like. They look like V's. Let's do that one more time with something with x squared. So again, we're going to take an input. We're going to say that y is going to be equal to x squared plus 1, and then I'm going to have my output ordered pair. Okay? And if you just want to make a table with x and y, that's okay too. Okay? I want to show you all the steps here. So my input, let's start here. Let's start with -2. So y is going to be equal to -2 squared plus 1. -2 squared, careful with this, -2 times -2 is positive 4. So the answer here would be 5. So this is -2, 5. Okay. For -1, y would be equal to -1 squared, which is positive 1 plus 1, gives me an output of 2. So that's -1, comma 2. If I plug in 0, that's 0 squared is 1. Plug in 1, watch what happens here. That's 1 squared is 1 plus 1 gives me 2 again. And when I plug in 2, I get 2 squared, which is 4, plus 1 is 5. So we see another pattern happening in that I'm getting the same answers over and over again. So we got -2, 5 right there. -1, 2 right there. 0, 1 right there. 1, 2, and 2, 5. Okay, so almost a V, but it's not completely straight. I made this graph a little bit big. In fact, if I plugged in 3, I would get 10. And if I plugged in 4, I would get 17, which is now a little bit off the graph. And if I plugged in -3, I would get positive 10 as well. So we get a nice graph that looks kind of like a curve. Okay? And as we'll see in a later chapter, this curve has a name, and it's called a parabola. But even if we didn't know that, even if we didn't know what x squared was going to look like, okay, we have this graph that gives us a nice smooth curve. Okay? And our got it problem, let's see what happens with x to the third. Okay? So x to the third plus 1. So I'm just going to make a 2-column table here, x and y. Ooh, ooh. Terrible, terrible column. All right. So let's plug in -2. -2 times -2 times -2 is -8 plus 1 is 7. Okay. -1. Sorry. Plus 1 is -7. -1 times -1 times -1 is -1 plus 1 is 0. 0 times 0 times 0 is still 0 plus 1 is 1. And then positive 1 gives me 2. Positive 2, that's 8 plus 1 is 9. Okay, so you can see what this is going to look like is 2 down 7, -1 to 0, 0, 1, and then 1 is going to be 2, and then 2 is going to be 9. Okay, so I get a graph that looks a little different, and what my cubic functions look like is it looks like a little curve like that. Okay, most cubic functions are going to look kind of like that. Okay, which is almost like what a parabola would look like if this side was flipped over this side. Okay, and we'll talk a lot about what functions look like and what different things look like later on. But for now, realize that any table can get you a graph. So graph each function rule. I don't want to go through all of these, but plug this in, you'll get a line, you'll get a line, you'll still get a line here. Okay, here you're going to get a nice little curve. Okay, so if you need practice graphing, um, and a good app to help you graph is a program called Desmos. If you haven't heard of it before, it is an online. There's a web interface. You can download an app for iOS and Android. Both excellent. Uh, it is an excellent graphing calculator app. So if you don't have a graphing calculator and you want to see what these look like, feel free to download that app. It is Desmos. Okay? Free graphing calculator. Okay? So the function rule, 18 plus 1.5n represents the height h in inches of a stack of traffic cones. So make a table for the function. So we can do that. We can calculate all these different heights. Suppose a stack of cones to be no taller than 30 inches. What is a reasonable graph for the function rule? So for that one, when I graph the function, okay, I'm going to get a nice little line, but this is going to be a discrete function because I can only put I can't split the cones up into different parts. Okay. So tell here these are better problems. Tell here whether the relationship be represented by a continuous or discrete. Number of bagels remaining in a dozen depends on the number that had been sold. Usually, stores don't sell you half a bagel, so this is going to be discrete. Gas remaining in a tank of gas grill depends on the amount of time the grill has been used. Okay, so you when the gas is on, the grill is burning. You can shut it off in 1 minute, 2 minutes, 30 seconds, 20 minutes. Okay, it doesn't matter. So that is going to be continuous. Right? So it depends on the situation. So these two would be discrete. This one continuous. Your friend graphs x plus 3 on the right. The error is that he should have connected the dots. Because unless you have a real world situation where you can clearly see what's going on with the function, always graph as a line, always graph continuous. Okay? And that was 4-4, graphing a function rule.